Thank you, Javier, and thank you very much, of course, for inviting me here. It's always lovely to come to Vigo, especially when it's such wonderful sunshine. It's always a great pleasure also to talk about something that's very dear to my heart, and I've been working in deep water sedimentary systems for many years in many different parts of the world, so it's a pleasure to share some of that with you. I didn't know quite who I would be talking to, but I thought I'd take the opportunity of broadening the topic a little bit and focusing to some extent on social aspects, political aspects, environmental aspects of studying the deep sea, as well as on some of the key scientific points. I only have, I understand, about 3 hours to talk. I'm joking. Because I don't have so much time to talk, I'm going to just touch on a few topics. But please, if there are any questions, of course, I will amplify and expand subsequently. So, first of all, let me thank the various people I work for, Heriot-Watt University. I'm part of the Edinburgh Collaborative for Subsurface Science and Engineering with Edinburgh University, the British Geological Survey, and so on, who are all acknowledged there. I should also acknowledge some of the photographs taken by Javier or Javier's colleagues and students crossing dangerous tracts of the ocean. What I'm going to talk about then is, first of all, just set the scene with global viewpoint of where the world is at and why we might be interested in the oceans and the deep oceans. So first of all, some challenging aspects about the present world. Then I'll focus on 3 or 4, I think, deep water topics: downslope systems, along-slope systems, the open oceans, chemogenic metalliferous sediments, and then pull together with some concluding remarks. The rather beautiful medusoid jellyfish that you see there is just to not only to entertain your eyes, but the next time you see that jellyfish, I will nearly have finished. So you can relax at that point. Right. If we go back some 40 years, just over 40 years, when human beings first went to the moon in 1969, it was really at that point, and not much before that point, that our global view of the Earth changed completely. It was the first time that really we had seen it from space, that we'd taken photos of the Earth from space, relayed them back to people. And I think at that time, and from that time onwards, people really began to understand how small and how finite and enclosed the Earth was. How it was, in fact, a very fragile ecological system and a complete unity, not separate mountains, separate countries, separate seas and so on, but seen from space and in the grandeur of space, a single ecological unity. It was dominantly ocean and atmosphere, and a little bit of land as well, where humans being lived. We also realized from that stage onwards that the resources were therefore limited, that the environment was therefore limited as well, and that those were really going to be our 2 defining issues for the forthcoming century. And the oceans are key in both of those, and the deep oceans in particular. And that's what I will focus on in a moment. But first of all, 1 or 2 more general points. We live in an energy-hungry world, and that's something that everybody has said, of course, and there are many diagrams of this sort. This one shows global oil consumption from 1990 through to estimated 2020. And what you can see is that all the graphs of energy use, this is in million barrels per day of oil equivalent, they're all going upwards. Perhaps in Western Europe we're moderately increasing. In Middle East, Central, South America, moderately increasing in use. America, of course, increasing enormously from a relatively high starting point as well. And most dominant on that graph, of course, is developing Asia, India, China, Southeast Asia in general, on a hugely upward increasing trend. So, an energy-hungry world. 90% or over 80% of that is still fossil fuels, oil, gas, coal. Very few renewables, nuclear, globally, in actual fact. And an interesting fact I always think is that humankind consumes in 1 year what it has taken 1 million years for nature to produce. So it's a finite resource. However much we think we have, it is very definitely finite. We also live in a resource-hungry world in many different ways, many different resources. And that's driven by population growth, for one thing. And global population, we know, will grow to over 9 billion people on Earth by 2050. India and China alone will grow by 21 million people in the next 10 years or 8 years now. Now that is really quite a staggering figure. And I liken it to Edinburgh, where I live. That means it's a big city, it's the capital of Scotland. 50 new Edinburghs every year, 50 new Edinburghs between now and 2020 must be built, just in China and India. I don't know how many Vigos. Vigos may be a similar size to Edinburgh, but that's the sort of population. And it's not only population increase, you've got to build the cities for people to live in. You've got to have all the heating, you've got to have all the electrics and so on, for that sort of increase of population. It's driven not only by population increase, it's driven by consumerism. Not only are we increasing in population, but we're increasing in wealth and well-being and the amount of things we consume, the cars, the telephones, the computers, all these sorts of things. And even if we go, for example, to electric cars rather than oil-fired, petrol-fired cars, then we've got to think about kilograms of copper that are used. This hybrid car, the Toyota's Primid hybrid car, that's part electric, part gas, uses 50 kilograms of copper. If you go to all electric cars, each car that you have is 100 kilograms of copper. So where is that copper going to come from in this resource-hungry world? The resource-hungry aspect is driven also by development needs, and particular development needs of the poorer nations of Africa, of Southeast Asia, and so on. And on this graph, for example, you can see the use of fossil fuel per capita on this scale and the GNP per capita on that scale. It doesn't matter the figures, but what you see is a very clear trend from the poorest countries in Africa, Chad, Ethiopia, Mozambique, and so on, through to India, to China, to the much more developed nations, the USA, Canada, Spain will be in somewhere in here as well. So as development proceeds, so energy use proceeds, so any of the other resources that we use will increase as well. And, of course, the world will develop, and it should develop, and that's the direction. So there's going to be more stress on both energy and other resources worldwide. Then if you think of the environment and the environmental limited aspect, of course we know that the Earth is warming rapidly under this cloak of greenhouse gases that we're putting up into the air, into the atmosphere from burning fossil fuels, from various other aspects of our lives. And everybody knows the results of that on things like climate change, the prediction or the actuality of climate change from 1800 through to the present, through the Industrial Revolution and the present day oil revolution, and then the predicted increase in temperature. Just in the 20th century, last century, over half a degree global temperature increase. The warmest decade on record, the 1990s and the 2000s. Sea level up by 10 or 20 centimetres through that time and still increasing. Ice caps melting. Extreme weather, such as the weather perhaps we're having outside, becoming more frequent, and so on. So all these things point to it being a challenging world in which we live. Challenged by this growing population, challenged by the development needs of that growing population, challenged by the fact that the resource base is finite, challenged by the effect we're having on environment and global warming. Such that my daughter, some years ago, and she hates me putting this picture up, but said to me, when you think about it, Daddy, your generation, our generation, or the older ones amongst us, has really left the world in a bit of a mess. What are we going to do about it? And it wasn't so much a challenge, it was, she was reflecting. This is a serious situation. So, this brings me to the oceans, and we could turn, and people are indeed, turning to the oceans to try and solve some of those challenges, solve some of those problems that we know we will face in the future, or our children, our children's children will face in the future. Because the ocean is 71% of the Earth's surface, 60% of that is over 2,000 meters deep. So the deep oceans, the really deep oceans, are the dominant part of the world. And really, it is very, very little known. I think largely we can say it's an unknown frontier for science. It has unknown potential for energy or other resources. And we are having unknown effects as we probe into that abyss. And that's where, and that's why, the likes of you and me are most interested in the oceans and in learning about the oceans, the scientific understanding of the oceans. So I'll move now on to my 4 different ocean topics. First of all, the downslope systems. And it's what I started out looking at in my PhD in Dalhousie many years ago, looking at all those sediments that moved from the shallow water into the deep water, into that realm that we still know very little about. And I'll also highlight a few aspects from the research over those past years based on the different drilling ventures, the international drilling programs, starting off with the deep sea drilling program many years ago, the ocean drilling program, and then most recently the integrated ocean drilling program that Javier and I have just returned from. But this takes us back, first of all, to drilling into turbidites. I'll explain turbidites in a moment. I expect you all know about them. But drilling into these deep water sediments in the Indian Ocean. And this was an early expedition of the ocean drilling program with the JOIDES Resolution drill ship into the central part of the Indian Ocean. And the reason for doing that, one of the reasons for doing that, was to look at what happened when India collided with Asia and pushed the Himalayas up. It started, these are paleo-oceanographic maps, it started something like 120 million years ago when India was there, more or less just detached from Antarctica and Africa. And then it proceeded to move north across what was the Tethys Ocean. There was a big equatorial ocean, the Tethys Ocean. And it progressively moved north, here it's going, moved north through that time as the ocean closed, Tethys Ocean closed, the Atlantic widened, and then India began to collide about 40 million years or so ago with Asia, and pushed up the world's mightiest mountain chain, the Himalaya range, with all the major peaks over 8,000 meters in height. But one of the best ways to understand that uplift and understand the effects of that uplift is actually to drill the results of that uplift in the deep oceans. And as it was being uplifted, so weathering stripped away the sediments, moved them down the river systems, the Ganges, the Meghna, the Brahmaputra, the Indus river systems and so on, and moved them then out across the shelf and into the deep sea, ultimately building up the world's two largest submarine fan systems. This is the Bengal fan, highlighted in yellow here, through the whole of the extent of the northeast Indian Ocean. So this is Sri Lanka, India, and about 3,000 meters in length from its proximal end to the distal end, 600 to 900 kilometers in width, sediment thicknesses in the slope region at over 15 kilometers in thickness. And where we were drilling, at the toe end here, it was still 3 kilometers of sediment thickness. And all of that, 2 million square kilometers of sediment with that thickness, having eroded from the uplift of the Himalayas over the 40 million years or so of history. We, in fact, I won't go more into the science than that, but we, in fact, drilled here several sites, and we drilled about a kilometre, just over a kilometre, back into the sedimentary record. And we found that that was 20 million years of supply of material from the Himalayas. And supply of material in these processes known as turbidity currents, principally, big, muddy, turbulent flows that started here in a big canyon across the shelf, and then proceeded down the main active channel, which is highlighted there, 3,000 kilometres, and dumped their load. Now, interestingly, you would think that after 3,000 kilometres of transport, it would just be very, very fine, thin-bedded sediments that got there. But some of the sediments that some of the single deposits of turbidites that we drilled through were from the floor here to the ceiling. 3-4 meters of sediment thick, deposited by one single flow that had travelled 3,000 meters down the channel system. Quite staggering if you think about that sort of process. And deposited, I say, pretty much instantaneously in a matter of hours or maybe days, but from one single event. We found many other things. Some had come from here, some had come from Sri Lanka. We could detect the type of sediment from Sri Lanka. Some had come from India across here. Some had come even locally from the Afanasi-Nittican seamount and come in that direction. But the dominant supply was from the north. Now, these turbidites, going into turbidites, are something that I've worked on for many, many years, and they come in all sorts of different shapes and sizes, and they're one of a family of downslope processes. And the viewcraft here shows this sort of family of processes from the shelf through slide and slump processes, through muddy debris flow processes that then evolve into turbidity currents. And it's these turbidity currents, clouds of mud and water, that can race thousands, hundreds and thousands of kilometers across very, very flat, low gradient sea floor. When you look through this sort of succession, if you look through what's deposited here versus here versus here and downslope, we have a fairly standard trend of change of sediment type. Now, these are not from the Bengal fan, but from similar deposits that outcrop on land. And in the more proximal area, we get the chaotic slump debris flow mass. Then within the channels, very, very coarse-going gravel, sand deposits, and so on. And as you go further out across the fan, across the Bengal fan system, you have graded, laminated sediment, classical turbidites of this sort. And then in the very distal area, we move into very, very thin-bedded silt mud turbidites that were very typical. And those things were very typical in the distal Bengal fan, as well as these very thick sand through to mud turbidites that I was talking about. Now, fascinating science, and one can go on studying these things forever and a day, but they do have interesting applications. And where I'm working now, and have worked sometimes in the past with the oil industry, they are particularly interesting in that aspect. Because there are currently, and still counting, probably now over 1,500 different oil and gas fields that are found in those sorts of turbidite sediments around the world. Not the modern ones, such as on the Bengal fan today, but buried ones, ancient ones. Something like, as I say, counting as of about 2000, there were 1,300 to 1,400, excluding many of the ones from Russia and China that we didn't know about. So we're up to maybe 1,600 individual fields that are in turbidite systems. Some of those are really true giant fields with over 500 million barrels of oil in place. They occur in all the established basins around the world, the North Sea Basin, California, onshore China and so on, and progressively into new offshore frontier basins of current deepwater systems. And this view from the north coast of Spain are typical of the turbidites that are deposited, stacked together, and it's this sort of deposit that can give rise to the reservoirs for oil and gas fields in many parts of the world. Sometimes the sands are thicker, sometimes thinner bedded, as they are there. I should mention in passing also, there's a huge amount of effort at the moment also looking at turbidite sediments as a possible place to take carbon dioxide out of the atmosphere and sequester it back into the underground subsurface turbidite systems. So both in terms of holding the oil and gas and then putting carbon dioxide back, these turbidite systems are particularly interesting and important. There are many different basins around the world, frontier areas for hydrocarbon exploration, all along the margin of South America, all along the particularly West African margin here, now also some off East Africa, the Indian margins, Gulf of Mexico, many different parts of the world. People are looking for these sorts, exactly those sorts of sediments in deep water. I'll just show you one example from offshore West Africa, the Angola Basin. And this is, the top view here is a map, a plan view of the subsurface down at a Oligocene age, something like 30 million years or so ago. So it's within the section, subsurface, and it's just amplifying certain characteristics of the subsurface. And you can see in that plan view a very distinctive channel, a deep water channel, not a river channel, but a deep water channel, very similar to the one that I showed across the Bengal fan, for example, very similar to the ones across the Indus fan, the North West Indian Ocean, and so on. And it's within these systems, scale here of 1 kilometre, so the channel just a few hundred metres in width, and it's within those systems that the sandy reservoir turbidites are typically trapped, and that's the sort of system that people are looking for in terms of potential reservoir. The cross-section, this cross-section here on the seismic profile shows in detail what that channel fill looks like. It would be that sort of system, just in the channel segment. There are many other examples. The lower Congo Basin, again offshore West Africa, a complex of these meandering channel systems, overlapping, intertwining, different phases of channels, very much like fluvial systems, but these are in several kilometres of water depth, or were deposited in several kilometres of water depth. So those, and the particular fill of those channels, and again a seismic cross-section across one of these, showing the particularly high reflective seismic characteristic of those systems. That's what is being targeted, and that remains as one of the challenges for science and for industry to understand these channel systems, what they look like, what their geometry is. They're not all the same sort of meanders. Some are more straight, some are gently sinuous. What's their overall geometry? And what about the sediment fill? This is a schematic model through a few tens of meters of channel section, showing slump material, very coarse-grained gravel material, some thick-bedded sands, some thinner-bedded turbidites at the top, and to try and understand to what extent channels behave to this idealized model, conform to that idealized model, to what extent they vary, is one of the challenges that faces turbidite science at present. Right, I think that was enough on downslope systems. Let me turn briefly to the along-slope system and looking at the types of sediment deposited by these along-slope processes. So instead of the downslope movement of material through these gravitationally driven processes, we're looking at the along-slope movement of the along-slope processes and the along-slope movement of material along the deep water continental margins as well. These then relate to an overall circulation system within the ocean basins. So instead of looking at the downslope, gravitational driven, we're looking at a long slope movement of the oceanic water masses and the sediments that they carry. The one that I'll focus on just a little bit is a rather smaller system where the deeper water has been generated in the Mediterranean Sea, has come out through the Straits of Gibraltar and through the Gulf of Cadiz and veers up into the North Atlantic. And this, of course, is where Javier and I were most recently on another ocean drilling program looking at the results of some of those currents. But they're everywhere, wherever we look. And just before getting into the detail of this system here, let's have a look at what we know through the North Atlantic first. And the currents that we're talking about, we tend to refer to as bottom currents or contour currents, as they follow along the bottom of the seafloor, hugging the contours. And they're semi-permanent, very variable in nature in terms of velocity and direction, but generally thick, moving masses of water with overall relatively low velocities, but velocities that are of the order of a few centimeters per second, but that those velocities can be increased very considerably where they abut against very steep continental margins, such as along here or along the Greenland margin, or where they pass through narrow oceanic gateways, like the Straits of Gibraltar or the Denmark Strait between Iceland and Greenland up there. And as the water narrows or is pushed against the continental margin, so the velocity increases and can increase to as much as nearly 3 meters per second. And that sort of velocity is capable of moving very eroding sediment and moving very coarse-grained material as well. Where they sometimes change direction or slow, such as around the current that comes out of the Denmark Strait along this margin, around the southern tip of Greenland and into the Labrador Basin, they can build big, thick mounds of sediment known as contrite drifts. And this is a section of the Iric Drift on the southern tip of Greenland, several hundreds of meters, about 500 meters thick there, about 20 kilometers in width, and several hundreds of kilometers in length. So a big mound of sediment built up by these bottom currents. Now, what we were looking at was the system that came out of the Straits of Gibraltar at the base, flowing along the bottom. The Atlantic water flows in at the surface, the Mediterranean outflow water flows out at the base, and then moves around the Gulf of Cadiz in this sort of pattern, indicated by the dark blue, spreading into, separating into one or two different strands as it moves to the west and ultimately to the north, around Galicia, past Vigo and on up to past Scotland, where I come from. But as it moves out through very high velocity here, generally lower velocity as you move in this direction, and splits into several strands and builds up big mounds of sediment, like I showed you for the Irish drift. And some of these mounds of sediment were our targets for this particular drilling expedition that we were on. Of course, the area has been, and I know many people in Vigo have been very active in terms of understanding and mapping the whole of the Cadiz margin, and so in advance of the drilling we had a fairly good idea of the different elements of that margin, and I'm not going to talk through that complexity by any means, but simply to say proximally erosive, scoured, rocky substrate, then into very sand-rich deposits moved by these currents, and the currents moving off down through the channels, again carrying sand with them, and then depositing more mud-rich units the further away from that Straits of Gibraltar. And we drilled a series of sites from proximal through the channels to more distal and around the margin here on the Portuguese margin. One of these big drift systems is shown here, the Faro drift system, and we drilled in a couple of places down through here, almost a kilometre of sediment in some of those holes. And overall, we recovered 5.5 kilometres of sediment through these contorite drifts. And it really is, it was before this stage, the world's premier contorite laboratory in which to understand this type of sediment, and now very much so, having drilled 5.5 kilometres through the system, recovering over 4 kilometres of contorite sediments. We have a much, much better understanding of the system. Now, again, I don't have time to go into the science in great detail, but just quickly to say we were able to look at the small scale, look at the contorite sediments as opposed to turbidite sediments I was talking about before, the contorite sediments and the cyclicity that we see in contorites from mud through silt to sand, back to silt and mud, over, and the scale here is 10 centimetres, over a few tens of centimetres. So examine that idealised model and test the idealised model, and in fact found that the idealised model was very fit for purpose, and we drilled through hundreds upon hundreds of these different contorite types of sediments. Just before we pass on from this, I should say our interpretation of that sort of cyclicity was that was related to bottom current velocity. So long-term change in bottom current velocity from lower velocity depositing the mud through higher and higher velocity depositing the sand, and then back to lower velocity. So looking at long-term fluctuation in bottom current velocity. And indeed, we found many, many examples of these idealized sequences, but we also found that many of the examples, many of the sequences were curtailed in one way. They only had the top part, or only the bottom part, or only the middle part. So they were not by any means so uniform in characteristic, and they varied very much in scale, from 5 centimetres to 7 metres in variation. They varied in periodicity, one cycle every 4,000 years to one cycle every 8,000 years was perhaps about average, and we're still trying to understand quite what the driver is for that type of cyclicity. It's sub-millennial scale driver of some kind. We also found, in addition to many, many examples of the standard contorites, we also drilled with difficulty into much more sand-rich systems, and I think I'll perhaps I'll show you in a moment, some of these sand-rich contorite systems. Another thing, before I go to that it enabled us to do was to look at the larger scale through some of these drift systems and look at the larger scale cyclicity, what we call seismic cyclicity. You can see the light, dark bands, or more translucent to more reflective seismic bands on a scale of a few tens of meters, a seismic scale, and to try and understand what that looked like in the sediment record and what the controls were. And I'm not going to be able to answer that for you now because it's still something that we're very much working on. Our interpretation before going was that, again, it was related to large-scale velocity, long-term velocity increase, but in this case over probably 100,000 or 200,000 year type cycles, from a transparent facies that was more mud-rich to a reflective facies that was more sand-rich, and a discontinuity surface with highest velocity of currents. But this is still being worked on. What we did find, and what we tried to drill into but had great difficulty drilling into, was some of the sand-rich elements close to the Gibraltar Gateway. And at the surface we can see, from bottom photographs, we can see examples of large dune crests here, ripples at the surface, cascading down the dune front. And these features are several meters in wavelength. So from the one side of the dune up to the crest and down there, it would be something like the length of this desk, perhaps. So all the way along here, increasing to about the desk height and then plunging off down at the other side. And for bottom currents to form that sort of scale of feature, they need a relatively high velocity, and we'd estimate something like 1 meter per second to create that. And then the little ripples over the top created by bottom currents flowing at much slower velocities. So an interesting mixture of different velocities that we're getting through the system. If we, again, this is from before going, but we found exactly the same in drilling through several hundreds of meters of these sandy contrites, but in taking cores from the surface, near the surface, we find very, very sand-rich, laminated and cross-laminated sand-rich contrites. Now these are relatively little known prior to the expedition, and we now, I think, are going to have a much better understanding of what they look like, how thick they are, what their different characteristics are, and indeed, are these the deep-sea reservoirs of the future? Are these things going to replace the turbidite sands as the prime reservoir target in the future? And I think the answer is they have a great potential. The future will see. Right, I'm sorry, I'm going a bit too slowly. I'll speed up. Open ocean systems. I just want to probably hit one point within the open ocean systems. So we've looked at the downslope, we've looked at the along slope very briefly. What happens just in general in the open oceans? And of course what happens is that we have all sorts of pelagic organisms, planktonic organisms that live and flourish in the surface of the water, in addition to anything that's blown in by winds or swept in by surface currents and plumes and so on. And this stuff settles gently through the ocean basins to land on the seafloor. Some examples, and I always rather like this one. This is a satellite view of eastern North America, Nova Scotia there, Newfoundland there, and this huge cloudy, milky white mass of material in the surface of the ocean is made up of microscopic scale nanofossils. Now, these are tiny little plates of calcium carbonate created by a unicellular organism, an algal-like organism, that lives in its countless billions and trillions of individuals in the surface waters. Each of those little discs is of the order of a micron or 2 or 3 microns in diameter. That means you would fit something like 40,000 of those onto a pinhead. And yet they live in such profusion that at different times in Earth's history they have fallen and been preserved, fallen to the seafloor, been preserved on the seafloor to build up huge thicknesses of fine-grained limestone or chalk. And the nanofossils, those skeletal material, is what forms dominantly these chalk sediments that we find everywhere around the world. From many different ages, these particular ones are from the Cretaceous, late Cretaceous period, about 80 to 60 million years ago, 65 million years ago, when the world's oceans were at their highest, the climate was warmest, most of the world was underwater, and these types of things were deposited. In addition to the chalk, you can just see the dark bands in the chalk there that are made up of these flint chert nodules, a different type of organism, but a planktonic organism. But I'm not really going to talk about those. I'm just going to talk about one episode of when things, if you like, go wrong or go right in the planktonic open ocean world. And it's what I refer to as the Black Death. And around 95 million years ago, this is a reconstruction of the world. Remember, India was still, had only just detached from Antarctica and Africa, was beginning to move across. But at that particular time, there was this broad Tethys Ocean, and the planktonic material that was floating around settled to the seafloor, but in many cases, not only the skeletal matter, but the organic rich material was preserved. So the organic, soft organic tissue was preserved. And this formed organic rich sediments. And the dark red blotches that I've drawn all over here are different places we've drilled through the ocean floor, or we've explored on land, rocks of exactly that age and exactly that time. All over the world, we have preservation of organic matter in what we call black shales. So it's an episode that we can recognize wherever we are, more or less wherever we are in the world. And this, for example, outcrop of limestone and black sediment in central Apennines of Italy is an example of exactly that mid-Cretaceous, about 95 million year old series of black organic rich sediments. A very early expedition I went on with Glomar Challenger, a deep sea drilling project, was to the South Atlantic Ocean, the Angola Basin. Here's Africa, this is the Walvis Ridge, and we drilled in about 5 kilometers, 5.5 kilometers of water depth at about this site. One of the targets was to go through Cretaceous age rocks of that particular age, and we drilled through 1.1 kilometers of sediment into the ocean crust, and at about this depth, just below the red seismic lines there, we went into the black ocean basin. And this is me in a younger period of my life with other sedimentologists, but we've been pushed aside by the organic geochemists who are very anxious to get their hands on the black sediment, this Black Death, the black shales. Organic rich material, mid-Cretaceous age. A very intriguing story behind its origin, and of course with huge repercussions for global resources. Mostly it was these sorts of organisms, again these are microscopic, sand-sized diatoms in fact, and these were very dominant in the planktonic seas. It's the organic matter associated with those that was preserved, and if we take a thin section of some of the sediment that we drilled through, it's like that. This is probably 1 millimeter or so in thickness. Little thin silty stringers, and all the dark brown orangey colour is organic rich sediments that's preserved along with mud and so on. It's that material that gives rise, after burial and heating, essentially burial and heating, to between 50 and 150 degrees centigrade, it gives rise to oil. Little bit higher temperatures, and it gives rise to gas generation. So that's the dominant source of oil and gas. And in fact, that mid-Cretaceous episode is the dominant source rock for many of the oil and gas basins around the world, many of the ones in the Middle East, North Africa, West Africa, sourced from the ones I was showing you, sourced from this sort of material. There are other periods, black shale periods around the world as well. But there's a lot still to be understood about how those occur in deep water, why they're preserved, and so on, that we haven't got time to go into. But a very interesting new direction for science of these things is actually to look in detail at this sediment, because in the States in particular, it's those mud deposits that when they're squashed and squeezed become shale that have actually generated gas, but the gas can't escape out of them. So you have big, thick units, kilometers thick in many cases, of deep-sea mudstones, shales, that still hold gas. And in the States, they've discovered this in a big way, and being America, they drill everything they can find. The only way of getting the gas out is to drill horizontal wells through the shales, and then hydraulically fracture them. It's called fracking. So they break the shale apart, and the gas flows into the borehole, and they produce it. So now, something like 20% of North American gas, and increasing, is produced from these shale gas resources. It's a huge direction of research for the oil industry, and hence also for academia, to understand these shale resources, these black shale resources. Right, finally, sorry, what's the time? Finally, chemogenic resources. I'll just show you some quick slides of these, and hopefully one movie. But in addition to all these sediments we've talked about, and in fact, where you have an absence of sediments, perhaps they're swept away by currents or whatever, an absence of sediments and a recirculation of fluids through the ocean crust and through the sediments, you can get chemogenic material. This fantastic sort of cathedral of structures comes from the deep sea floor, from a mid-ocean ridge setting, and it's made up of chemical sediments that have been precipitated from black smoking chimneys. And I'm not sure if I can get that to work, but if I can. This is a film of a black smoking chimney. The sort of things that are the sorts of process that's happening in the middle of the oceans at the present day, on mid-Atlantic ridges, building up these fantastic metal precipitates of different enriched metals: iron, copper, nickel, zinc, lead, gold, silver, all sorts of different metals being precipitated from these hot fluids. They're often coming out at several hundred degrees centigrade, cooling instantly in the deep sea at near freezing point, and so building up these chimneys. Associated with them, you also have, oops, I need to get out of that. You also have all sorts of strange organisms, these fantastic tube worms, little white crabs, sea fleas, giant mussels, strange things living in hot temperatures, several kilometers below the surface, so no sunlight at all, different form of life. But why am I talking about these? It's not something actually that I've researched myself, and most of these views and the the movie that you saw comes from a colleague of mine, Steve Scott from Canada, who's been doing a lot of research into this new type of resource that was only discovered in the 70s, these black smokers. But since then, in the 1970s, since then, we found many, many examples around the oceans of these types of sediment. They're often associated, and they were first found associated with mid-ocean rifts, where oceans are spreading apart, basalts intruding, and so on. And the metal sulfide deposits associated with those mid-ocean ridges gave a completely new insight into an understanding of the massive sulfide deposits on land, such as the major one at Rio Tinto and associated deposits in southern Spain. And so this sort of system is a new analogue for those types of deposits. But they're not only found in mid-ocean ridges. In fact, they seem to be even more prevalent in back arc rifts, spreading rifts closer to the continental margins. And and you have these fantastic structures formed. And many, many examples have been discovered from different rift systems associated with some mafic intrusions, some dikes, some basalts and so on, recirculating fluids and escaping fluids, building up these cathedral cities of metal-rich sediments. There's very active exploration for these things as a new resource in many parts of the world. This particular map shows the Western Pacific region, where off Korea, off Japan, off China, off Australia, off Papua New Guinea and so on, there have been many finds made, and various companies, Nautilus Minerals, Neptune Minerals, Blue Water Exploration, have all formed in the last couple of decades to exploit this new resource. An amazing potential for, as I say, for copper. And this particular one, the Manus Rift off Papua New Guinea, is going to be the first one that is mined. This slide was a couple of years old. It may even have been mined by now, I'm not sure. But licenses had been granted, plans were well afoot, and Neptune Minerals were going to, Nautilus Minerals were going to mine this, the Solawa 1 deposit. And it had, they'd estimated, 7.2% copper by weight. Lots of zinc, lead, silver, 6.2 grams per ton of gold. Now that's between 3 and 6 times the amount of those minerals than in some of the very famous onshore Canadian or Japanese deposits, metal deposits. So, fantastic resource, and of course, a lot of it, and a lot of it still to be found. Right, I'll skip through Cyprus, where we can find it on land, and finally get to the figure. Only 5 minutes. It might even be less. I just wanted to wrap up, so I very quickly looked at some snapshots of the science, but to come back to the theme of, so what? What does this mean in terms of social, political, environmental aspects? Clearly, there's a fantastic magic and mystery of science of the unknown, the sediment, and of course these wonderful organisms above, the anglerfish, bioluminescent red shrimps and so on, that float around in this subsurface. But what are the social issues to address? And I started at the beginning by saying, as far as I could see, there were issues around resources. They're finite resources, and we, as a human species, are using them up at profligate rates. We potentially are degrading a fragile environment and ecosystem. We have the problem of trying to produce resources and energy for this burgeoning global population, and also supplying the rightful developmental aspirations of much of the world that doesn't have the quality of life that you and I share. And I can't see what that is. It's probably an environmental issue down there. So the key questions for us with respect to the deep oceans, I believe, because we're only just beginning to explore, exploit, develop, understand the deep oceans. So we still have a chance to influence what we do. And I think we should be asking the questions, yes, there are these fantastic new resources in the deep oceans, the deep sea oil, the deep sea gas, the deep sea minerals, and many more that I've not mentioned. Should we exploit them? You know, it's a simple question. Should we or should we not? If we do, what should we? They're scant, they're limited, however abundant they seem to us, they are limited. What should we use them for? Should we, for example, use the oil to make petrol to fuel aircraft and cars, or should we reserve it for making plastics, if you like, or all the other things that we use it for? What else can the oceans provide? I haven't even mentioned the rare earth elements that the Japanese in particular are going into the deep oceans to look for, the new types of bioorganisms, of microbes that may inform and help medical research and so on. So what else might they provide? And can we protect the ocean environment for the future? We haven't done a very good job of protecting much of the terrestrial environment. We should be thinking about protecting the oceans, or should we? Clearly, there's a lot of confusion, a lot of debate in the literature about renewable capacity of the oceans, energy resource lifetimes, climate change, about global warming, about sea level, about ocean acidification, about dumping our waste annually into the oceans and so on. There are lots of different factors to take into account, and I'll just finish by saying, sort of from a personal perspective, these are some of the solutions or the things we should be considering. We should reduce our use of resources by conservation, by other means. We should control the carbon dioxide emissions. We should tackle population issues and poverty issues, developmental issues. We've got to manage that global ocean space, the deep ocean space in particular. And in my view, and as scientists, we clearly need to understand scientifically these oceans much, much better than we do. And we need some kind of environmental tax on resource exploitation, on oil exploration, on gas exploitation, on mineral that is fed directly back into the universities for scientific research in the future. So let me finish there. Thank you very much, and sorry to go on for so long.